Hello, my name is Ali Mohammadi, and in this presentation, I'm going to introduce our novel algorithm that is a hierarchical multi-branch deepfake detection network, or HMBDDN. This project accomplished by Professor Nalini Ratta and I at State University of New York at Buffalo. Let's start with definition of deepfake detection and what is its application. Actually, as it is indicated on this slide, whenever you need to check if an image created by artificial intelligence or human, you can use your algorithm. And if algorithm is trained well enough, it is going to detect if that sample is fake or not. And why we need such an application? Actually, recently with the rise of good generative models, some people with bad intention actually abuse those tools to create some um misinformation and manipulate people's mind and damage society. And it is hard to detect the generated fake samples. Therefore, we need to create robust algorithms to address these problems. So if you look at these samples, one of them is fake and another is real, but it is really hard for us as a human even to detect it. As you see, the left one is the real, but it was hard for us to recognize at first. Um, what I want to talk about, I want to point out that in the recent literature, most of the researchers are interested in using transformer to create their majority of them to create their deepfake neural network algorithm because transformer is effective. But problem with the transformer is it is not computationally efficient, and sometimes it is time consuming and needs a high amount of memory. And for that, we propose an algorithm that is created to solve data imbalance problem and to help the discriminator to generalize well for unseen data. And to do that, we are introducing some mechanism in our architecture that actually performs a multi-level embedding transformation and at the same time targeted augmentation. And by doing these two, actually, it automatically also reduces the effect of noise or bad data inside our data when we are augmenting and increasing the size of our data. And this is also another problem that other researchers were trying to work on that, how to avoid increasing the size of the out of distribution data while yeah, we are generating some augmenting and generating some sample to help us to get help from them. So our architecture is actually in this slide. We are proposing this architecture and this idea. And I'm going to go back to explain the component and how they are organized and the way to be efficient and help us with video effective video processing. But I want to point out that the inner side of this, the discriminator part that is connected to the K-means mode and connected to ResNet. These three components, the combination of these are one of the key novelty in this method and algorithm. And let's start from introducing the components. In the first component, We have a video processing mechanism that receives the two class of the video, real and fake, and extract the frames for those videos and use mobile net to find the region of interest. After we find the region of interest, which is the region that human images inside, because we are not interested into the frames that are not included human and included tree or car. Then after that, we utilize BlazeNet, which is much better for detecting the face itself. Then we perform localization here to only focus on the faces that we want to train our algorithm on. Then we can have effective algorithm by focusing, effectively train our algorithm by focusing on the image itself. After that, when we do that, we build our training data set, and our training data set after this the is the data set of the images that we extracted from the exact face region, and now we have that data set. We move forward. We have that data set. We move forward with training the discriminator part. Before doing that, first we fine-tune the pre-trained version of the ResNet, and after training for fine-tuning is over, we feed training data again and extract the embedding from last four layer of the ResNet layers. And now the output is the four different version of the uh, training data in different abstraction level. But still, we have imbalance two classes that their embedding is also imbalance. And for that, actually, we apply Smote to augment the data, augment the embeddings that we extract from each embedding each layer of the resonance, and move forward with aggregating all of the uh, data, all of the embedding and concatenation layer of our discriminator. And the following is going to be only three linear layer, which is very easy to train and optimize. And after training is done and we save the best trained model, we use test data set to perform inference and analyze the accuracy or use it for detecting the fake faces. And so we for training we use 70% of the training data for training, 10% for validation, and 20% for um, testing and inference. And we use two NVIDIA T4 GPU and 29 gigabyte of RAM. And also in the results section, we performed the ablation study to see the effect of the smote, to see how smote is effective. Also, what is the difference when we train our final discriminator on 50 epoch or with the smote or without the smote. And we realized that even with the lowest amount of epoch, 50 epoch, our algorithm without even augmentation reached 97%, 98.90% accuracy. And when we increase it into the 300 epoch and the uses mode, reaches the highest accuracy in this research, which is 99.10% accuracy. And in terms of computation cost, actually our whole smooth process for all training data takes only less than 3 minutes. And for each training epoch, we have approximately less than 10 seconds. So it seems that this model is quite cheap, and the result is repeatable for the cases that we don't have expensive computation power. And comparing with the state of the art, as it is indicated, our model with 99.10%, even without this mode, 98.94% percent accuracy, while we are not using complex and expensive transformer network. And the other algorithms with using transformer network from 2024, they reached the lower score, and it shows that our algorithm is less computationally expensive and reached a higher accuracy. So, as a conclusion, it is it is obvious that if you apply some approach to reduce the negative effect of imbalanced data and try to find a way to generalize your data and your model, then it helps you to have less computationally expensive model, and at the same time a strong model and well generalized for the unseen data. And yeah, based on the current result that we have and the motivation, we are motivated to apply these algorithms to optimize to create a real-time application for this, and also apply our algorithm to larger data set. And please feel free to contact us for any question that you have, and you're welcome to ask any question. And if you're interested for collaboration, we're going to be pleased to see your email. And thank you for watching.